Hello and welcome to today's webinar, From Data to Decision, Smarter Traffic and Urban Mobility Planning, part of Connect Me's Asset and Mapping Events, Harnessing Location Intelligence series. My name's Aaron Addison. I'm the Executive Director of the World Geospatial Industry Council, or WGIC, and I'll be moderating the event and hosting the Q&A later in the presentation. Before we get started, we'd like to run a quick poll of the audience to find out where you are and from where. Here, pull this up. We're running a quick poll of the audience to find out where you're from and what industries and sectors you work in. The poll has popped up on your screen, hopefully, so be sure to fill it out and hit submit. We'd like to have an interactive session today, so please enter your questions into the Q&A space provided, located on the bottom navigation bar of your screen. There's no need to raise your hand. Just post all questions to the Q&A space, and presenters will respond to all questions at the end of when all the presentations are finished in the panel discussion. Also, please be sure to participate in any audience polls as they pop up throughout the event. For information about speakers and an event agenda, click the Resources tab at the bottom of your screen. We've also shared some useful links in the Resources section, which you can access at any time. This session is being recorded and will be available for download on demand after the event. You will receive an email notifying you when the recording is available. We'd like to thank our webinar series sponsors, TomTom, for making this educational opportunity available to you. Today we have three featured speakers. Besides myself, we have Pete Costello, the Senior Account Manager, Public Sector for TomTom. We have Vijay Sabawat, Principal Data Scientist at Parsons, and we have Amir, Ghods, Founder and CEO of SMATS Traffic Solution. If we get into the session overview and the topics for today, we've understood and heard feedback around public agencies facing growing pressure to improve traffic flow, reduce delays, and plan smarter infrastructure to justify decisions with data. This spans from federal grants to public accountability, but suffice to say, nobody likes to be slowed down in traffic. So there's a real pain point here, and I think we'll learn some ways to address that and improve that situation. However, without reliable, scalable traffic analytics, agencies oftentimes struggle to identify the bottlenecks, optimize signal timing, and prioritize investments. This leads to inefficient operations and decisions, limited visibility, and missed opportunities to improve safety and mobility outcomes. Integrated location and traffic analytics is key to improving not only performance, but safety and resilience. Traditional methods, such as manual counts and models, are often outdated and don't really capture the current conditions. Infrequent and disconnected from real-world conditions, floating car data helps agencies to make faster, evidence-based decisions using real-world traffic insights, not only at intersections, but across corridors and regions. With case studies and examples, today we will cover why evidence-based model mobility beats legacy methods. We'll look at key traffic planning challenges and using congestion, origin, destination, and junction insights in planning workflows. Our hope is that we'll be able to help you figure out how real-world traffic data can uncover hidden inefficiencies in networks, to evaluate and improve junction and corridor performance, practical ways to integrate traffic insights into planning workflows and models, and examples of how agencies are actually using data to support more informed and accountable decisions. Before we get to that, though, let's take a look at those poll results and see where everyone is from. So it looks like we have a healthy percentage of about half of our attendees today are in local government and scattered out through other sectors as well. You can read down, you can show the poll results and scroll down to read through all the results. So now let's go ahead and get started so that we have as much time as possible later for the discussion and the Q&A. 1 second here while I pull up the rest of our document. So my first speaker for today will be Pete Costello, the Senior Account Manager for the Public Sector at TomTom. Take it away, Pete.
Thank you, Aaron. Appreciate the introduction. Thank you for your kind words. I'm Pete Costello. I'm based in Orlando, but today I'm in our U.S. headquarters in Lebanon, New Hampshire. And I'm pleased to see some snow out the window and a little winter wonderland preparing, the holiday spirit for sure. So it's great to be with everybody today. Thank you for your time. Thank you for joining us. I'm going to talk a little bit about TomTom and what we're up to in this traffic and mobility space and some of the solutions and tools that we bring to bear. As you can see on your screen here, uh, TomTom, you may, remember and know us for the GPS devices that, were stuck to windshields, and we pioneered that in 2004, and we're a routing and navigation company at our heart, and also mapping. So we have a map called Orbis, and then our best quality traffic measures to deal with these traffic issues, these urban mobility issues, that I'll talk about here in a moment. So Orbis Maps, as you can see on the left-hand part of your screen, we joined with Amazon, Microsoft, and Meta back in 2002 to create the Overture Map Foundation. These companies all had a lot of resources they were putting into mapping, and we pooled those resources together to create the Overture open source map. Each one of the founding members, and there's additional members that have joined subsequently, but each one of the founding members brought mapping resources to the table and made that available in an open source way and continue to update that map, both some core features and then some extra kind of features to that map. That's our base map at TomTom for Orbis. But we've built up a whole bunch of layers on top of it. As you can see, 80 plus layers are available of location specific information. What's kind of interesting to, the transportation world are some of the layers that you see on the screen here for automated driving, for those automated vehicles that need to know what's going on the infrastructure because there is not a driver there to observe them. We're cataloging all that information from LiDAR and other images, with even pavement markings, where curbs are, where traffic control devices are, and things of that nature. We also have a layer for for driver assistance to keep vehicles in lanes to reduce the possibility of crashes. And again, routing and navigation, the core of our business, and the roots of our business. We're very excellent on doing that. We have a whole layer that we built up over the past couple of years for EVs, where the chargers are. Is somebody plugged in now to deal with those range anxieties that those electric vehicles have? And then the traffic layer. My career has been focused on intelligent transportation systems here for the past 25 plus years on traffic and operations. So I'm really encouraged by the kind of data that we provide, not just in the US and Canada, but around the globe. And then the other interesting thing about Orbis is you can bring your own agency data and have it interplay, and you have some flexibility with the map and things of that. The thing that surprised me when I came on board at TomTom, I learned that we update this map globally, and that's in 235 countries and territories. So we cover the whole globe with this digital map. Every week we update that. We're constantly making edits and updating the map. It's the freshest map out there. And as you can see with the partners we have in Overture, you can kind of think of Orbis as a choice. If you don't want to use a Google map, you prefer not to, that's kind of how this group came together, to offer a choice for Google Map. So I have a quote here from Manuela, who's one of our SVPs, Senior Vice President. She presented at an automotive conference just a few months ago, big automotive conference in Munich, talking about TomTom. We don't just build maps. This is a foundation for open collaboration, for interoperability. We want to move the industry forward. We're really creating an ecosystem. That's what we're about. And here are some of the partners in our ecosystem. On the right-hand side of the screen, you can see our automotive and truck OEM partners that we do a lot of work for. That's a lot of the focus of our company, for the routing and navigation for those automated vehicles that these truck manufacturers and personal vehicle manufacturers are working on. There's some that you can't see. We can't name all the companies that we're working with, but we're working with over 30 OEMs on automated driving features. And on the left-hand side, there's some agencies that you're probably more familiar with, some companies that you're more familiar with, and we're very pleased to have one of our partners, SMATS Traffic Solutions, that is going to be speaking after me to talk more in detail about how to use these tools and this data. And you can also see in the top left, if you are in an Uber or even a Lyft, we're providing that routing and navigation to those people. So we get a whole bunch of floating cars that are telling us where they are, their speed, location, heading, and some other connected vehicle kind of data from them. We aggregate that all together. And here's some of the innovations that we're working on. As you can see, automated driving we know is coming. We want the vehicle to be aware of vulnerable road users. We're painting digitally the lines on the infrastructure, which you can kind of see here, the pavement markings, the crosswalk, the bike lane, all these kind of things, and the path of the vehicle to work on this automated driving, as I mentioned, for a bunch of automotive OEMs and truck OEMs. We have something called MoMA. I thought it was a Museum of Modern Art, but here at TomTom, it's mobile mapping as a service. We have vehicles, and actually there's a couple in the parking lot here that are outfitted with a whole bunch of sensitive cameras that drive each year over a million miles of roadway, gathering these point clouds, the LiDAR clouds, the camera, to bring that into our map for specific uses for some of those OEMs that are manufacturing vehicles. One thing that we're doing, we're based in Europe. Our headquarters is in Amsterdam. We have a project in the EU called In-Lane. We're seeing a lot of requests for lane by lane navigation. So to do the navigation, what lane to be in, to make the turn, to get ready for where the interchange is, where the ingress and egress is on limited access roadways. We're also next year going to work on lane by lane data, the speed data, on a bunch of roadways, starting with limited access roadways, but eventually to all roadways. We'll be reporting lane by lane. This is just an example of what we're doing now down in Miami, Florida. They were one of the first places in the country to have express lanes on an interstate. And as you can see here, the two innermost lanes, if you will, there's actually two lanes in each direction that are express lanes in this area, and three general purpose lanes. So we were able to separate the express lanes from the general purpose lanes, and there's only plastic pylons in between those lanes. So you can see that we're well on our way to getting this lane by lane data available. I mentioned earlier our best quality traffic measures. So we're gathering all these individual points, aggregating them together. There's an organization called the Eastern Transportation Coalition that has a traffic data marketplace, and they test this data. The most recent test was about a year ago in Atlanta. Happy to report that TomTom, our data, which we provided through one of our distributors, and that's part of our ecosystem. We work with distributors and solution providers. So Carto provided this data to the coalition. It's the lowest latency data, about a minute, which is really good to get that information from the vehicle, process it, and get the speed data back out on that observed speed on each roadway segment. And we also had the lowest average absolute speed error across these speed bins, as you can see here. So the best quality traffic measures as backed up by the results from the Eastern Transportation Coalition. I'd be remiss here in 2025, as we're heading to 2026, to not having a slide or two on AI. A couple months back, we made an announcement that we have this Model Context Protocol server, MCP server. It's a standard. Not sure if you've heard it before. A lot of the transport industry, people I talk to, it's a new thing for them. But basically, it's using an agent for AI that would talk to our MCP server organize all the TomTom information that that agent wants and provide it back and forth instead of like a typical chat GPT or large language model going out and grabbing all the information. The MCP server organizes all our information to have a timely response, and we'll have some announcements on that in the coming year related to that with some of the partners that we're working with. Another thing I wanted to share with you all, one of our partners and also a partner in the Overture Maps Foundation is Esri. We do a lot of work with Esri. We're the base map for Esri as well as Bing Maps. And with Esri, we have this partnership. If anybody closes a road in ArcGIS, we get that information as well as Apple. The folks on the Esri team here at TomTom say that Waze gets it too, but the second link there publicly only says TomTom and Apple. But I think we're in need in the U.S. and maybe Canada as well for a national road closure and lane closure database. And I think this is a step in that direction. The last innovation I'll share before talking a little bit more in detail what to do with the traffic data is a product that we released a couple months ago in Europe called Tom. It's a little device, as you can see there. It blinks in different colors, and it also has an audible sound. It works in conjunction with our app, and we have a free app available on the iPhone and Android. Just search on TomTom. You can start using our data locally, but this device works globally, although we're selling it right now just in Europe. But I was able to get a device that works here in the U.S. The red, as you see, one of the alerts there, that's of a queue, a traffic jam to warn people in advance to slow down. It alerts to speed cameras, which are obviously very important in Europe. And then the lane by lane information that we're collecting. If there's a broke down vehicle or something like that, we'd see yellow there. And then that orange warning is if you're going a little too fast. So I only see that once or twice, but but it's a very good way to keep people focused on the driver function. And talking about this data, where we have it and how we provide it, we have real-time live traffic data in 84 countries. So like I said, US and Canada, and then 82 others. 650 million plus devices are reporting us this positional information as often as once a second. So we're processing tens of billions of these data points every minute. Every 30 seconds, we say, here's what we're observing out on the roadway network for speeds. Again, that low latency that I talked about earlier. And across the US and Canada, we're getting data from 1 in 4 vehicles that are out on your roadway network, which is, again, best quality that's out there for sure. On the left-hand side, we could take that probe data plus other information. So journalistic data is things like the work zone data exchange information that some states have, as well as other crash and incident information and work zone information that states have. Sensor-derived observations are from the vehicle themselves, from cameras and the sensors on the vehicles. We integrate that into our Fusion engine, as well as active community input. That Tom device I showed you has a button on top. You can report incidents as well, again, in a safe manner, so you're focused on driving. We also have traffic moderation. We have a lot of AI tools looking at these inputs on the left side into our traffic fusion engine, but we also have people doing the quality control process to ensure that we're getting the best information into the Fusion engine. And then we have speed profiles, almost 300 different profiles. We profile each segment and what kind of attributes that segment might have. So we bring that in as well. And then the output every 30 seconds, again, fresh, best quality traffic measures out there on live traffic speeds, and then incidents, the jams, and where congestion is. So we'll talk briefly here about some of our real-time and live traffic services, and then talk about our historical. So traffic incidents and flow, again, it's available in those 80 countries. We have location referencing. We're very good at that because we are a map maker. We can do conflation between different maps and do all those kind of things, and make this available in industry standard feeds. And it's not just used for traffic operations and traffic management centers. We do a lot of work in Auckland, New Zealand with the authorities there. And they, in their traffic management center, have a transit folks that are there as well that use that real-time information to make changes to their public transport network and some of the routing and things like that to route their buses away from, congestion incidents and things of that nature based on our data. We have another product called Area Analytics, and that is based on the work that we're doing on our traffic index. So this is the results from last year, our 2024 traffic index. Within the next month or so, we'll have our 2025. I don't know the exact date that's going to be released. It could be here in December or January. Of the most congested cities across the globe, we had a list of 500 some, as you can see. London, Milan, Paris, Brussels, they're among the most congested cities. And we looked at this area analytics product when New York City earlier this year, in January, transitioned to their congestion pricing. We looked at the congestion the year before. We saw congestion levels in 24 of about 43% in this area. That's the lower Manhattan area where they implemented the tolling to get into there at certain times of day. And then you can see the first 3 months or 2.5 months really reduced a bunch down to 30% in this area. So a big improvement when New York City unveiled this congestion pricing scheme. We can kind of see the levels here of the congestion from the previous year in 24 into this year. You can kind of see that initially it's low, but it does kind of bounce back. And we compared it to the year before. It almost bounced back to normal here. So I guess there was a big hullabaloo about the congestion pricing, but it looks like people didn't pay for it for a while and then said, "Hey, it's worth it." And then the agency is collecting some of that information now, and the money as well related to that. I'll talk about a couple of our historical products and a couple of our real-time products here in a moment. Traffic stats is the historical data that we get from all those probes over a period of time. On each road segment, you can see the speeds that we see historically. This is a stretch of road in Tampa near the airport on the left-hand side of the image. You can see all the percentiles and the speeds. This is available in as small as 5-minute intervals back in history, a number of years for sure. We can do OD analysis. So we have a stretch of road here. We can see that 100% of the vehicles were on that segment. That's good. 60% of them left from that road heading to the northwest in the red there. About half of them entered that segment from that freeway coming from the east, and about a third from the freeway coming from the east. Half came from the west, and the rest came from the south. So we can do this for a segment level in percentages, and then of course we can do the vehicle counts. So 5,648 vehicles we saw there, and then you can see the true numbers of the vehicles that went through this segment. And we could do that for areas as well, not just segments for origin destination. For route monitoring, it's basically a travel time between a point A and point B. This is in Las Vegas. At the north is the convention center, and the south is the airport. I have a bunch of my colleagues going to Las Vegas for CES in January, so we'll be making some announcements. It's very interesting how CES has become a very automotive focused show. So a lot of our own automotive team will be there, and I guess they're interested in getting to the airport in a timely manner. So we have this route that we can collect this information in real time, and then it's archived to see how that travel time changes, and the queues and the delay change over time. Similar to that, we can look at any junction, signalized or non-signalized, to look at the intersection and see where the traffic comes from and where it goes through the intersection, the turning movements, the delay. We can do the queue back to 2 kilometers, so we can really get a good view of queues that are at intersections. And then you can get all the various data and see where the turning movements go and all that. And then the delay, and then the typical delay, and the travel time through those intersections. The good news about all these tools, we have them available at what we call our Move portal. You see the QR code and the link there to get the 30-day free trial of our area analytics to look at congestion in areas, traffic stats for historical segment by segment, OD for segments as well as areas, route monitoring for those travel times, and then the intersection analytics, which we call junction analytics. I also mentioned our app, so if you want to see how our data is performing in your neck of the woods, please download and check our app out. And again, we're a mapping company, so Rock, our VP of Map, says everything starts with the map as a canvas, and then everything else is just happening in the map. So that's kind of our philosophy. And here at TomTom, we stand ready for the future that you all want to build, and we want to keep everything moving. So that's the conclusion of my presentation, and I'll stop sharing my screen, and I'm going to introduce our next speaker, who is Amir from SMATS Traffic Solutions. And I think Amir will be coming here into the webinar. All
Thanks
right, thanks, Amir.
everyone for joining this webinar. My name is Amir Ghods, and I'm the CEO of SMATS Traffic Solutions in Ottawa, Canada. And today, I'm going to cover a bit of more broader use case of the connected vehicle data based on TomTom data. The title, we call it Accessing Network-Wide Transportation Analytics via Connected Vehicles. Just a little bit background about SMATS. We are a traffic data analytics company, and we use various data sources in our product called iNode application. And then we convert the data, whether from sensors or from connected vehicles or floating car data, to actionable traffic insights for various use cases, including public sector, cities, municipalities, consulting firms, and also port authorities and terminal operators who are involved in the supply chain ecosystem. Just a little bit of our customers we have served, a select list of them, as I mentioned, public sector in Canada and US, consulting firm, and also people involved in the supply chain, such as ports and terminal operators. Basically, anyone who needs land traffic data for improving the traffic efficiency, planning, operation, or safety use cases. So we have served those clients with the data that we provide through our application. Just a bit of deeper dive into the app iNode. We are mainly using TomTom data as our main data source for probe data or floating car data. We are an integrator and a distributor of TomTom's traffic data analytics products in North America. And through our app, we provide the insights and metrics such as travel time, speed, volume, signal performance measures, origin destination analysis, safety analytics, and also metrics such as annual average daily traffic, vehicle miles travel, and daily movement counts. And the app comes with the visualizations, API, dashboards, automation for different use cases in traffic operation, planning, and also safety. Just a bit more deeper dive into the TomTom data characteristics. As Pete mentioned, we have done a few validation that's going to come in the next slide, but the data characteristic is very important in any traffic data analytics projects. So we have seen a very consistent, impressive penetration rate with TomTom, both in Canada and the US. As Pete mentioned, the historic and live data are both available. The historic data goes 10 years back for speed and travel time from yesterday. So there's a daily update, which is great. And also 2 years of origin destination data and 3 years of volume estimation data that we have built on top of TomTom data. There is we call it the high resolution or high fidelity data in terms of the granular segment selection in the map when you run analysis and studies. And that comes with the high resolution GPS data from TomTom providers, which are normally between, 3 to 5 seconds or never less than 10 seconds update interval of the location of the car. That brings a lot of advantage to running different type of analysis in micro level and also macro level. So the data also has the connected car data characteristics, and what it means is that it's not a cell phone based data like a location based services that you might have multiple cell phones in the car, and it brings like a double counting issues to the data. So this actually doesn't exist with the TomTom data, which is mostly the data is associated with the vehicle, not with the person. So as I mentioned, the data quality, we did some validation in Canada and the US, and that includes metrics such as penetration rate, travel time, speed metrics, and also volume estimations that we built on TomTom data. The penetration rate, it varies between different road classes, but as Pete mentioned, so they are with a range of 30% or more. The data that we have seen in Canada, Alberta, so we are seeing, penetration rate of up to 29% on road class 0, which is mostly highway systems, and then down to 15 to 18% for lower road classes back in 2024. But I'm sure if you run this study now, so the sample size is growing. There are more newer cars coming to the market with TomTom data and also more providers. So the penetration is now even higher. So what we also see that in the US penetration rate is slightly higher than Canada, and also west of Canada, for example, Vancouver, we have seen penetration rate up to 40%. Travel time is another metric that you can reliably use for floating car data. So we compare the Bluetooth-based travel time data, so the graph on the right top, versus the TomTom route monitoring. Travel time information, there was around 95% accuracy, matching the Bluetooth data. Speed also is being widely used for safety projects that we are involved in. So whether it's average speed or 85th percentile speed, and we did a few verification against radar counts and tube radar speed data and tube measure the speed data, and they all come very close to the what TomTom segment level report as 85th percentile speed or average speed. We also extended the metric to the volume-based metrics. So for turning movement counts and mid-block counts down to 15 minutes interval. And we recently completed a verification study with the Maricopa Association of Governments that we were able to estimate the volume using the sample data from TomTom floating car data with an RS score of roughly around 97%. And then the same volume metrics on the monthly average daily traffic and also weekday and weekend traffic was also very close to the ground truth data that we capture from the field devices. The historic data is, as mentioned, available through the TomTom platform with an everyday update. So you can run on a study for yesterday. You don't have to wait a couple of months to get fresh data in the system. The metrics include travel time, speed and delays, and volume estimation, and origin destination analysis. There's a lot of use cases that we are seeing with the historic data, including congestion scanning for networks, running before and after studies for signal retiming projects or traffic calming safety related projects, calibration of the macro simulation and macro simulation models. Another safety use case that we are seeing a lot, cut through analysis that complaints come from the citizens. Their neighborhood is being used as a travel pass when the congestion is high on the main road, and also other travel demand management studies and land use studies that we are seeing in various projects. Live data, as mentioned by Pete, is also a great offering with an every minute update, low latency. The metrics include travel time, speed, and delays, whether on the main roads or the intersections through the junction product, and also incident feeds that is available as a live. Use cases can be citywide congestion monitoring, monitoring work zones, events, and also ad hoc signal retiming projects, and also emergency response. So I'll walk you through a couple of projects that we have done with the consulting firms or the cities or municipalities or DOTs, just to give an idea how these metrics and tools out of the floating car data from TomTom can be applied to practical projects. In this slide, you are seeing a screenshot from Toronto in Ontario that we have a toll road called 407, which was a paid road, still paid for a major section, but the east section of that became free to the public. And the ministry wanted to know whether making that toll road free to the public, whether it reduced the congestion from the parallel load, which is the Highway 401, as you can see on the south of this screen. So the origin destination analysis was very helpful to see if there's a shift of traffic patterns from the 401 to 407 because of opening this section of the toll road to the public as a free with a free access. So that was done for the Ministry of Transportation Ontario through a consulting firm. The other example is a road safety project. So when the MPO, the Broward County through SS4A project, they were interested to get the top 10 high-risk corridors. And the most important metric was to have access to a network-wide 85th percentile speed data. And we know that in traffic safety, 85th percentile speed is important compared to the average speed, which is available into some platforms, but it's not really a good measure for the safety tool, for a safety analysis. So we provided the speed data to TomTom for this project, and also in parallel, the quality of the speed data, the accuracy of the speed data was compared against radar counts for the select locations. And again, the accuracy was around 94%, which tell us, the speed data can be used for a wide network screening project like this, with a high confidence and to provide like a safety metrics and top ranking high risk corridors for SS4A projects. Another example of origin destination use case. So cut through analysis on the top that you see, a client in Quebec was interested to quantify whether there's a cut through happening accessing the highway. And again, because of the main road gets congested, people use the alternative routes, which are through the residential areas to access the highway. And with the origin destination tool, that was with a couple of clicks, it was very easy to run this analysis and provide the insight whether the cut through is happening and to what extent. The other application of the region-based OD was a transportation master plan, which was done in Ontario through consulting, where the zones are placed, the TAZ zones that are from the forecast models, and then the output is normally an OD matrix that you put into the model, and then the model can create a new forecast and new metrics for longer term transportation planning. We call it normally master plans. And then another live use case. So we are involved in a project near Windsor, Ontario. Is a long-term construction for expanding Highway 3. And we are involved in data collection, both on the travel time, monitoring of the segment, and also signal performance measure using junction data to make sure that the the travel time and the delays are being monitored closely, and then the detours that are designed are working properly, and to make sure if there is any adjustment needs to the signal timing are done on time thanks to the live data that we are capturing through TomTom. So recently we are more focused on the signal use cases. So we call it proactive signal traffic management using floating car data, which comes out of the TomTom junction analytics. So it basically provides all the performance metrics for the intersection without deploying any hardware. That includes, approach delay, travel time, arrival on greens, queue lengths, and also this data can be aggregated per movement, per direction, and for different time of the day. So it's a 24/7, 365 days live data, and then the app provides visualization, trend analysis, and continuous reporting. That's also done on the corridor level, where you are more interested in the progression improvements and progression quality, and that easily replace any manual GPS surveys that you might be doing before to getting the performance level on the corridor when there's a signal retiming project. So this data is also available on every corridor that you select, and for any direction and for any time of the day. So as Pete mentioned, everybody has an AI slide. So we are also leveraging AI with the network-wide floating car data. So there is more data coming. So there are more data to be processed, and at one point, the more data is great, but the interpretation and also analyzing the data gets more difficult. We believe that the AI can help. For example, for the signal performance measure analytics. So let's say you have around 200, 300 intersection you want to monitor, and you want to get insights to see what's happening. So then the linguistic model can help you come up with some questions that as a user or as an operator can ask. For example, we call it, as an example, focusing on 8 p.m. peaks. What's the normal days you detect in the data? And then the linguistic model go to the database and capture some of those movements and some of the days that the traffic is abnormal. So that helps with the answering some questions, because some people complain about congestion, and so that helps why this day was worse, whether the demand was higher or anything was failing in the system. So we think that the AI can help to analyze this type of big data pretty efficiently. The other example that we tried, so we said which movement gets the highest split failures, and then at what time of the day, and then looking at the database and the linguistic chat model. So it captured all the intersections with the highest split failures and which movement are happening, and at what time of day you have the highest split failure rate. So this AI was able to just start listening to the operator question and get the insights and the visualization they need on an ad hoc basis pretty quickly. And also another question, if you are involved in a retiming project and you want to make sure your AM peak and PM peaks for weekdays and weekdays are correct in your, let's say, synchro model. So you just can ask that questions, and based on the volume profiles that we have for the intersection, so the AI can analyze all the intersection and give you the information about what should be the AM peak and PM peak hours for your signal projects. So that's about my presentation for today. So this is our contact information. Please feel free to reach out if you want to have any questions or you have any projects to discuss. So now I'll invite the next presenter, Vijay Sabawat from Parsons, to come to the stage and talk about their projects related to floating car data.
Hello, everyone. My name is Vijay, and I'm a data scientist with Parsons, and I work in traffic operations and intelligent transportation systems, focusing on how probe data or connected vehicle technologies and advanced analytics can be applied to real-world mobility and safety challenges. Much of my work centers on turning complex transportation data into practical decision-ready tools for engineers and operators. I'm excited here to share some of those real-world experiences with you guys today. Let's get started. For the outline today, we'll begin with why the shift from data to decision really matters in motor traffic operations and why raw data alone is not longer good enough. Next, I'll briefly walk through the modern transportation data ecosystem, including like a high-risk data, signal data we are getting, connected vehicle data, probe data, fleet data, and a number of data sources that what we have and how all they fit into this ecosystem. Then we'll go take a look at how we transform the raw data into decision-ready intelligence through some of the processing, validation techniques, analytics, and visualizations. From there, I'll have some real-world examples that we did with the local agencies here that we are working with, where we are using this high-risk data and all the data that is and probe data that is available for us, and take some operational use cases and show how this approach is already influencing day-to-day traffic operations. And finally, we'll close with some key takeaways and what's next as we move towards more automated and predictive operations. So why data to decision matters, right? So most of the transportation agencies are now operating in a world dominated by probe data, large-scale telemetrics, where we are getting tons and tons of raw data, whether it's GPS-based travel data, connected vehicle messages, fleets, and third-party data analytics platforms. The real breakthrough today is not just that we are having more data, it's that this data is now accessible to for everyday engineers and practitioners. What once was required custom coding and database access and a lot of programming languages that one has to learn in order to understand what the data is providing. But through this intuitive probe data analytics platform, where users can filter corridors, visualize travel times, compare before and after conditions, monitor KPIs in minutes, which is really beneficial for all the day-to-day operations rather than which used to take for months. At the same time, the shift does not replace the advanced analytics, like for the researchers and whatnot. It enables it. Behind every visualization still sits that raw high-res data that remains fully available to researchers, data scientists, and model developers. This allows advanced users to develop new KPIs, predictive models, thanks to the new AIs and whatnot. We've got some safety indicators and come up with different control strategies without being constrained by predefined vendor dashboards. This dual layer ecosystem, simple analytics for practitioners and raw data access for innovation is what truly enables the data to decision paradigm. It ensures that the decision makers at every technical level, from field engineers to researchers to leaderships, all are working from the same trusted one data source, one true data source. Now let's go to what a typical modern probe data ecosystem looks like. So this is a diagram where it shows the ecosystem is structured from ground up and how it supports both everyday operations and advanced research from the same shared data foundation. At the left of the diagram are our data sources. This includes the high resolution data, which is coming from the traffic signal controllers, or probe vehicle data, mobile GPS data, location-based services, connected vehicle data, like for the BSMs, SRMs, SSMs, fleet and maintenance telemetry data for the AVL, for the snowplow tracking, fire, ambulance, all the AVL data that we have, and also a whole range of the cutting-edge new detection technology that we have at our signalized intersections, right? Like for the vulnerable road users. For pedestrians, the detection system could be both of the radar-based or the LiDAR-based technologies that are which are more available for the local agencies, for the agencies to use in the day-to-day signal operations. Each of these sources produce extremely rich, high-frequency data, but on their own, they tell only a part of the operational story, but not necessarily complete. So I think that's where the probe data operational platforms comes into picture, because this is the unifying layer that brings everything together. Here, data is streamed in real time, stored in cloud data lake, and validated for quality, processed in unified events, and transformed into performance metrics. This is where raw telemetrics becomes trusted and decision-ready information. In few years back, all this raw data is given to you to the practitioner, but the practitioner has to either master a technology or a programming language to understand what's happening with the data. But thanks to all the probe data, now all the data analytics is not necessary a whole for the most part of the time. All the metrics are readily available for the users to consume. And on the rightmost, we have the two main user groups, practitioners and operators, who are your traffic engineers, operational staff, maintenance teams, and these users are interacting with the system primarily through dashboards and operational metrics. So they see travel times, delay, queues detection, health, and priority performance in a visual and intuitive format, which is most important, right? And they can explore the conditions and compare scenarios, identify the problem without really needing to write a code or reviewing the databases. This is where the pro data analytics and the day-to-day operations really shine. And on the other side, where we have researchers, data innovators, like data scientists or universities, or really advanced data analytics team, where they really want to see the raw data and they want to get into the nuts and bolts of the data, and they are still be able to get the same data from the same platforms through APIs and other ways to get the data. This data could include time series logs, trajectory data, high resolution data, model training data. And this raw data is what enables the development of new performance metrics and predictive models, AI, ML applications, and the next generation control strategies. The most important concept this diagram communicates is both groups are powered by the exact same data foundation. So the practitioners are getting simplicity and the speed, whereas the researchers are getting the depth and the flexibility. And the agency benefits from innovation without disrupting the daily operations. This layered ecosystem is the backbone from a data to decision framework. Next slide is from raw data to decision-ready intelligence. Now, this slide summarizes at a high level how raw transportation data is transformed into the information that people can actually use to make decisions. First, data is automatically ingested from multiple systems, including the Pro platform, signal controllers, connected vehicles, fleet telemetry. The data is then standardized and quality checked, so users aren't working with inconsistent formats or unreadable records. And next is the key event and performance metrics that are generated. Things like travel time, delay, queues, and system responsiveness. Those metrics are delivered through visual dashboards and everyday practitioners, while the same underlying raw data remains available for research and data analytics who wants to go deeper. The important takeaway here is that the system is designed to be simple on the surface and powerful underneath. So now let's go to some of the use cases. And my use cases are very practical. Like, say, example here is a snowplow signal priority. This project is in Colorado, where we deployed a connected vehicle for snowplows along the corridors, so that during the winter season, when the snowplow operations comes in, you'll be using the connected vehicle technology for the snowplows to get priority or preemption. So that they can clean the corridors quickly without stopping, because these large vehicles have a tendency to have a very high deceleration rates and very high acceleration rates, creating traffic operations nightmare. So that's where this connected vehicle project came in. But in this particular use case, then how we use the probe data is like, it shows a complete, this particular use case shows the complete data to decision cycle, from identifying a problem to diagnosing the root cause and to implementing the verified operational improvement. The initial issue we observed was that even with the snowplow signal priority enabled, plows are still experiencing slow and inconsistent progression along the key corridors. From a field perspective, priority was active, but performance did not match what expected to see. We first identified this through probe data coming directly from the snowplow AVL system. This gave us real-time visibility into where plows were on the network and how fast they were actually moving. The probe data clearly showed us speed drops and reliability gaps at specific intersections and segments, which told us exactly where the problem was occurring. And to understand why this was happening, we turned into the raw CV2X messages and high-resolution signal controller logs. These data sets allowed us to see whether priority requests were being sent correctly and how signal system was actually responding to each location. So we did develop some in-house analytics and dashboards on Google Cloud Platform, where we aligned the probe data with raw system events and determined that RSU, the roadside unit map files and priority timing parameters are not fully optimized for the real-world plow operations. We then took direct operational action where we updated the RSU map files. So we basically extended the map file so that it has a longer time for the side streets to turn off and get the clearance interval going and get the main line green as soon as possible, and refine the priority durations in the controllers and validated those changes using both travel data as well as the raw SSM response timings. Yeah, and the outcome was measurable improvement in flow progression and corridor mobility during the snowplow operations. Next one is the detection failures from traditional metrics to a deeper insight. This is a second use case that highlights the complementary role of probe data and the raw event logs in the operational troubleshooting, where probe data gave us fast area-wide visibility, and event log gives us more precision it tells us exactly what needs to fix. The initial issue we observed was unexpected delay and inconsistent service across several intersections within the same area. Even though the coordination and the timing plans appear reasonable at a surface level, our first indication came from traditional ATSPM metrics, where we saw split failures, uneven green utilization, and degraded production. This was helpful as an early warning. It told us something wasn't working as expected. We then turned into probe-based travel time and delay data, which allowed us to quickly scan performance across the entire area. This is where the probe data really shines, right? It made it easy to see which corridors and approaches were experiencing abnormal delay and excessive delay without having to inspect each intersection one by one. That quickly narrowed our focus to a specific set of locations. And once the problem areas were identified, we used the raw high-resolution signal controller logs to perform precise root cause diagnostics. And again, we used some in-house built Google Cloud dashboards and some of the KPIs, and we drilled down to the detector actuations, phase calls, and service patterns at those exact locations and times. So this deeper visibility revealed missed calls and intermittent detector dropouts at a specific detector locations, which turned out to be the true cause for the performance issues. With that level of precision, we were able to take very targeted operational action. Maintenance teams were dispatched directly to the specific detectors and given the specific configuration settings, and we were able to go up and running pretty quickly. And once the repairs and everything was done, we again looked back into the probe travel time trend analysis, raw detector actuations, and ADS-PMs to make sure everything is working as expected. And this use case clearly shows us how probe data makes it easy to identify problems across larger areas, and how raw event log gives us the precision needed to fix the exact issue. Next use case is more on the use of LiDAR and the vulnerable road user safety. This use case focuses and shows and how advanced LiDAR-based detection technology allowed us to move beyond cons into actual behavioral risk. The original issue was we were concerned about wasn't just how many pedestrians or cyclists were crossing. It was how safely they were interacting with the traffic. We had an incidental concerns and the field observations of near misses, but limited objective data to quantify those risks. So we used a LiDAR detection system where we were able to capture the high-res LiDAR data, high-resolution controller data, and the pedestrian and the cyclist trajectories, including the precise movement path speeds and interaction points with the vehicles. Most importantly, the system generated near miss and conflict indicators, which allowed us to objectively measure risk, not just volumes. Through vendor-provided cloud-based dashboards and analytical tools, we visualized conflicting heat maps, trajectory clusters, and near-miss frequencies by movement and time of day. This made it very clear where and when the highest risk interactions were occurring. Once those conflict patterns were understood, we overlaid them with the signal timing and phase activity and found that many of these highest risk interactions were occurring during overlapping or permissive movements that created the complex decision environments for drivers and pedestrians. With that insight, we took some measurements. We modified the pedestrian timing, adjusted the phase sequence, and refined some of the clearance intervals so that to reduce the exposure between the vehicles and vulnerable road users, like using the LPIs and whatnot. The outcome we are hoping is to be like a measurable reduction in near miss frequencies and a conflict severity along with improved predictability of pedestrian crossings and driver responses. Typically, to do any kind of this kind of analysis, it will take years, but not in this case. Like here, we are getting some real-time, near real-time data. The fourth use case, well, this was supposed to be led by one of my colleagues who was originally scheduled to present this evaluation. But the objective was to assess the TomTom's turning movement penetration and corridor travel time accuracy, and to benchmark it against floating car runs, Google Maps, and CDOT's ATMS and Wi-Fi readers. The study covered multiple signalized intersections and major Chicago corridors under different traffic conditions using junction level probe counts and carefully matched corridor segmentation. The results showed a strong turn movement penetration and excellent travel time accuracy, with R-square values nearing to 1 and errors were under a minute when compared to the floating cars, where the typical Wi-Fi readers and traditional ATMs showed significantly higher error. The key takeaway from this study was that the TomTom Pro data proved to be both accurate and operationally reliable, making it well suited for real-time monitoring, performance measurements, and before and after studies. This validation step is exactly what makes a probe data decision not just for the convenient. The data to the decision loop. So this slide brings all the use cases together into a single repeatable framework, what we call to be a data to decision loop. It starts with collecting the data from pro platforms, field devices, and connector systems. Then that data is then validated, so we are confident in its accuracy and consistency. Next, we analyze the data using dashboards, metrics, raw data event logs to understand what actually is happening out in the field. That analysis supports a decision whether it's a timing change or a detection fix or a safety adjustment or a corridor strategy. We then implement the change operationally, and most importantly, we remeasure the performance to verify that the action delivered the intended outcome. Every use case we walk through today, like whether it be snow plowing no priority, detection failures, or corridor operations, probe data validation, follow the same loop. That's what turns the data into a continuous measurable improvement, not just like a one-time analysis. Some of the key takeaways, the path forward. First, the probe data gives us fast area-wide visibility. It allows agents to quickly understand what's happening across an entire network without needing to inspect each location individually. Second, the raw event logs provide precision. When it comes to understanding exactly why something is happening, whether it's a detection failure, timing issue, or a priority response, the level of detail only comes from event level system. Third is the agency-led or partner supported analytics or the bridge, where the tools are built internally, delivered through a consultants or provided by vendors. They connect the systems that were not originally designed to work together and turn the disconnected or the siloed data into a coordinated operational action. And finally, the data-driven decisions are no longer theoretical. They are actively improving mobility, maintenance efficiency, and vulnerable road user safety today. Looking forward, the path is toward more integrated platforms, expanded use of advanced sensing and connected vehicle technologies, and a growing role for the predictive and the AI-driven analytics. This is the future of traffic operations, where decisions are not just informed by data, but continuously shaped and validated by it. That would be the end of my presentation. Thank you again for your time, and I invite all the presenters back so we can take some questions.
Thank you, everyone. And I know, as somebody who used to do traffic modeling, I certainly learned a lot in the days of sitting there with a turn counter or trying to desperately figure out how to nail down a rubber hose into the pavement. So this is certainly welcome. So we're going to move into our Q&A session where we can really have a discussion around some of these things. And I've jotted down probably 10 or 15 questions here that I want to know, but we also want to hear from our attendees today. So if you do have any questions or want to know more about a particular idea or point, you enter those into the Q&A so that we can get to those. But I think to start with, for me, one of the things that we like to do in these webinars is we'll have attendees that are maybe doing traditional methods with the counters and the hoses, and we talk about a lot of new technology sometimes, but we don't talk about how to get from here to there. And and so is this a scenario where if a city or an organization wants to move to sort of the state of the art around the floating method from the traditional counts, do they have to just give up on the old counts? Is there a hybrid solution? How do they make that transition from the way they're doing things currently and stepping into the not only the improved methodology, I think by any measure, but the additional analytics that would be afforded to them by moving to that new method? And maybe just ask Pete to kick us off on that, and our other panelists can join in.
Sure, Aaron, in thinking about that question, right, from where we are now to where we want to go with this new technology, I think both Amir and Vijay highlighted some of the comparisons and validation, right? So I would stick with your traditional that works for you and you're used to the output and everything, and then compare that to what you might be able to get with a floating car data technology plus the analytics software that Vijay and Amir were both talking about. So that's what I would say. Do a parallel and say, hey, and then you can also get to the cost benefit and the time and resources part of the equation as well. So I'm sure Amir and Vijay would like to add to that.
Yeah, in my view, the most important first step is to start with the real operational problem. not with the technology, right? Like, pick one corridor where, or one safety issue or one performance challenge that matters to both leadership and the staff. Then identify what data already exists to measure that problem. Often probe data or the basic signal data is already sufficient. And once you solve one problem end to end, right? Like, you start with it, what's the issue, and you solve it so that you have the end to end. Then it becomes much easier to scale that approach across other corridors and systems. So I would definitely recommend that.
Yeah, I think, from what we have experienced so far, it really depends on the metric you are interested in and what are the alternatives you have, right? So, for example, and also the quality of the data in your city or region or the road type you want to analyze. So we always talk about penetration rate. Um, so for example, it's like metrics such as, travel time and speed data. So, if you have like a 20-30% capture rate, that's statistically significant and you don't need to deploy any hardware. The only time that the things gets tricky is when you want to use the probe data for volume-based metrics. So that's when, right now the ground truth is always the counters. But when this is where the hybrid model comes in and the probe data will fill out the gaps in between. So you have your counter station, you calibrate a model, and we can expand it in other location using probe data, which is a great hybrid solution. So, but I would say, looking at your, the project type metric you are interested in, what sample size you need, and whether you need the volume data or not. So then I think you can decide whether the probe data is the right choice. We have seen in a lot of use cases, the probe data can complement the sensor-based data, and some other metrics you can replace it.
No, that's great. Yeah, that's good to know. As I'm thinking through sort of practical examples and transportation engineering and health and safety too, where you would want to use that approach. I think another thing I was thinking about, I realized many of the examples, maybe all the examples that were shared today, were in what we'll just call urban areas. Like what's the range here? Is this something that I can use in the suburbs? Is this something I can use in rural areas? Many organizations are looking at planning scenarios saying, okay, they want to put in a new subdivision here. What are the origin destination changes? What's the load during the school year, during summer vacation? Like, how are these things changing before they permit and give the green light to that development? And so can you give us some sense of the sort of the extent, and I guess this gets to appropriate use and fit for purpose around technology and things like this. But is that a valid use case, or am I off base there?
So I can start again, Aaron. I think certainly in urban settings, we have more vehicles, so more opportunity to capture data. And that's why I mentioned that 1 in 4, that's vehicles providing us information. That's certainly in an urban location, but even and probably suburban as well, where there's a good density of vehicles. But even in rural areas, I think it would maybe get down to 1 in 5. So we really do have a good penetration. We do have a lot of fleet and logistics. So Amazon Fulfillment is a customer, and they have trucks in neighborhoods, all across America and Canada, delivering packages. Uber as well goes to people's homes. Obviously, we do all sorts of privacy, measures because we are European. We go with GDPR. And I think to your example of the land use, we certainly see people looking at traffic and where they're coming from and going to, and seeing where there might be some opportunities. Maybe to change land use, I think that's a big long process, but but there may be opportunities to do that.
Jay or Amir, either one of you
Yeah,
want
I
to add?
think we have seen, I guess the origin destination, of course, is one of the main inputs for transportation planning. So whether there is a land use change or new development, I think a lot of traffic impact studies that are also in this similar category where the origin destination data can help, and along with the other metrics, such as the level of service now, what's the congestion level, and how it's going to impact the new development and make things worse. So I think that's we have seen a lot of use case of floating car data. Again, with the enough sample, so that's all doable.
Yeah, and
Yeah,
also the real value is that the rural areas often lack like dense detection infrastructure, right? So probe data becomes the most cost-effective solution, just to understand the corridor performance or the freight movements or travel time reliability.
yeah, I think that's a great point. Um, I think another area that's top of mind for many people right now is privacy, especially as it relates to technologies that are probing or collecting data automatically. I think in all three of your presentations, I saw a reference to data being anonymized. And I think one question that I hear a lot is, at what step in the process does that happen? How does that happen? When do I become anonymous in this equation? And so that I know that that's not going to follow me around or be used in inappropriate ways from how the data is originally collected. Can you guys shed any light on that?
So in the TomTom case, we anonymize at the source, as well. We know where the vehicle obviously begins a journey and ends a journey. When we're doing some analysis and tools, we cut that beginning and end point. As we're doing our intersection analytics, the junction analytics, we'll cut in the intersection as well. And we also see with some of our suppliers changing the vehicle IDs at certain periods of time. So yeah, we're not tracking you through the system. Again, if we're getting billions of data points every minute, it's going to be hard to track somebody. And like I said, we are a European-based company, so we adhere to GDPR, which typically is a much more rigid approach to privacy than we have here in the States.
No, that's fantastic. That's good to know.
And for us as a partner, so there's always a question about that, and the TomTom at source, address those I guess challenges with privacy and concerns. But again, the aggregated data is available through APIs, and that's what we need in the use cases. Not most of the time, I think 90% of the time, not access to the raw GPS data, which may pose some privacy concerns.
Yeah, and most of the probe data given to an agency or any third-party user application either through APIs, most of the time it's aggregated data. So there's no its data is always anonymous, and even at a signalized intersection, so all the detections, all the lidars or any technology that they're using, they're just detecting the vehicle. They're not really capturing the each individual person or vehicle.
Yeah, I appreciate that. I think that's a message we need to continue to educate people on, because I think there's a lot of misinformation out there about what's being passed through these workflows ultimately, and they are really just whether the IDs have been changed or any other thing. There's no personally identifiable information anywhere in that pipeline. We have a question that's come in from the chat. Which I hadn't thought of, but is a very, very big question, is what should municipalities be asking consultants for when they're seeking to implement complete street inventories using floating data? And so if you had the chance to talk to the city and say, these are the types of things you want to put in your RFP, what would you tell them? What would you say are the important points to make sure that go into that document?
I would say let one of the sophisticated consultants on the call here answer that first, because they'll certainly have firsthand knowledge of what the complete streets application is.
Okay, guys, you're on the spot now.
Well, so I would say think of this as five categories, or data, what kind of methods, safety, community, and outcomes, right? what exactly are you using for the data sophistication? Like, which probe data sources are you using and why are we using? Or like, can you separate local trips from cut through or like a regional traffic? And and like, how do you turn this floating data into like a data decision, design decisions? Like, how do you translate floating data into geometric design recommendations? Or for the safety analytics, like, do you go beyond crashes? Like, can you identify a speeding related crash risk, even where crash history is limited? Or for the community and equity, can they support public engagement? Can you translate floating data into community friendly visuals? Can you show how traffic calming will affect emergency responses or the transit? I think these are some of the questions that definitely help to understand, like, especially with the data, where it's coming from and how we are sending the message across.
Very good.
Yeah.
And
So,
and, and I would, Amir, I don't know if you have anything to say, but I would sum up from our point of view. Basically, we just observe the speeds. So I think we'd be perfect to, as Vijay was saying, look at the area, look at the corridor, and see what the speeds are. And then after the traffic calming, the complete streets are in, we can see the results in our data.
yeah. So one of the things with the completed street is, I think, having like a street shared among different road users, like a paired bikes. So the floating car data tells you the story on the vehicle side, which looks isolated, but it's not. So a lot of projects, you want to add a bike lane, you need to make sure the speed is low enough for a bike lane, otherwise is very dangerous. And then maybe you need to have some calming measure first. So we had a situation in Toronto, and during the COVID time, they put bike lanes, and at the end, they had to remove every bike lane because of the safety issues and congestion issues. And to find the rooms that there are, like we want to reallocate lanes. So if there isn't enough capacity for that road to add a bike lane, so the floating car data tells you there's an opportunity there. And of course, for the safety use cases, the speed is very important. And doing like a before and after. So after adding a bike lane, so but it's still like a travel time and the level of service for cars is still the same, that justify the decision, and also make sure the speed is also at the stage that it doesn't pose any safety risk for the vulnerable road users such as bikes and pets.
No, that's fantastic. I don't know if any of you have ever worked on HAL analysis for high accident locations, which are where you have statistically higher numbers of accidents than what should be happening in a given place. And then you look for engineering mitigating steps that can be taken, whether it's a grade change or speed change and stuff like that. And a lot of that work gets done by reading literally tens of thousands of police reports and trying to map out how accidents happened and stuff. I can really see a use case here for some of the flow data as well.
Yeah,
Uh,
Aaron, I can give some coming attractions if you will.
that's my next question is and I'm gonna roll two things here
Okay,
that give you a platform for that, Pete.
okay.
Uh,
But related to safety, we're looking at some safety applications based on that connected vehicle data, the harsh braking, and some of those other things, and have like a safety application or a series of
yeah,
safety applications derived from that.
that's great. And that again, that's a very nice segue into this. So I'm going to combine two things. The what's on the horizon question. What do you see coming? But immediately, when you see a technology like this, I think everyone's mind starts thinking about, well, if I can do that, can I also do this? And so, when Amir was talking about, um, some of the dynamic nature of the data, can I reroute an ambulance in real time based on the probe data to get to a destination faster? And that's in that health and safety bucket. But I could also see FedEx wanting to use it to, they instead of just sending the truck out in the morning and saying this is your route, how would that change? Oh well, they closed that intersection at 10 o'clock this morning. How do I reroute the rest of that day for that driver? And you can imagine, and snowplows, I think, were also mentioned. So that's another great example about how we do. I was thinking about your exercise, but also thinking about real-time dispatch of snow plows, not just for routing, but say, where is it actually snowing? And can we get a truck there? It's that sort of just in time delivery of the service, whatever that might be, which isn't really necessarily some of the traffic that we've been talking about. But again, people are starting to look at the future. So I'd ask each of you to sort of offer some thoughts on what you see coming.
So yeah, if I can start, one of the many layers in our map is weather. So yeah, we can definitely see. I'm based in Florida. I can see heavy rain coming. We could see snow coming here. So the thing that I'm really interested in is, and one of the things where I mentioned that we're focusing on an automated vehicle layer. I think what we need to do is maybe some work. Are the local agencies and the state agencies, the infrastructure owner operators, ready for these AV vehicles that are coming? Do they have the proper pavement markings and all those kind of things that are requirements for that kind of driving?
Yeah.
Yeah, definitely in the in this latest infrastructure, right? Like where everything is connected and automated world. Our snowplows that in the use case that I provided, it is connected to our network and it is getting the real time notifications on the weather information. It has onboard sensors and also getting from information from the meteorologist. So they know when the snow is happening at what locations, what corridors need are a higher priority corridor, and in the real time, they're getting the information on the congestions from our avial data or the probe data, and they are rerouting in real time as a use case that we are doing.
Impressive. Anything to add, Amir?
No, just I agree with Pete and Vijay on this.
Yeah, I think also on response, if we have an accident at an intersection, we know which fire department should be there. We know which emergency, and so are we close to being able to automatically dispatch without someone calling 911? Even if it's computer vision enabled along with that to verify all these different, and I think that's where the partnerships and things that you guys talked about in terms of integrated solutions comes in, is that there's no reason the stoplights can't call 911 and say something's changed about what's happening in this intersection, and maybe put a human in the loop to verify that. But I can imagine reducing those response times utilizing technologies like we're shooting for today.
Yeah, on that one, like we're testing new detection systems at a signalized intersection where they're actually looking for stalled vehicles. And once they do see the stalled vehicles, they're notifying the TOC with a picture of when it has stalled, for how long it's been sitting there. And with a human verification, they can call dispatch an emergency vehicle right away or like a courtesy patrol to remove it from the scene.
Yeah, absolutely. I mean, if it's a truck, send this kind of tow truck. If it's a car, send this kind of like we know so much information about those things that we can, there's all these opportunities to create efficiency. Well, guys, we're out of time. This has been a fantastic discussion. I thank each of you for your contributions and the insights that you were able to provide to us today. Thanks again for your sponsorship, TomTom. And really look forward to seeing where this industry goes, these applications evolve, because it's an exciting time to be working on these topics. So thank you again. Thank everyone online for your participation. As a reminder, this event is recorded and can be played back. You'll receive a notification when that recording is ready. And as always, be sure to check out the other webinars being offered by this series online. So thank you very much, and I hope you have a great rest of your day.
Thank you.
Thanks, everyone.
Take care.